Okay. Hi, I'm Charlotte Slaughter.
I'm Dara, and we're going to be talking about some simulations and experiments of periodic forcing on a granular system.
Okay, so first a little bit of background. Why do we care about granular systems? Granular systems make up the foundations of our planet and every other planet. So they're underneath buildings, they're underneath roads, train tracks, etc. And often they change properties when different forces are applied to them. So we're looking at how these granular systems change under periodic forcing. An example of this in real life is cars on a road. You've got cars which act as the periodic forcing on the road, and then underneath is a granular system that changes with it. And sometimes this forces the roads or sidewalks or railroads to break or crack. So we're trying to see how they are affected so that we can prevent this kind of thing.
So, since we know that a particle's ability to move in these granular systems is critically dependent on its ability to rotate, the main question that we're going to ask is what kind of information can we get about the rotational and translational displacement of these particles, and what can that tell us about how the system will evolve with time?
So we did this, as we said before, through both an experiment and a simulation. On the experimental side, our setup for this is we had a glass box with one wall that was oscillating connected to a motor, and inside was a fluid that was index matched with acrylic beads, and on top there was a weighted wall. So this system, and then we oscillated the wall multiple times, and the way we analyze this system is we use a 2D sheet of lasers on both sides, as you can see in the diagram, and it essentially lights up a cross-section of this system so that we can track both its rotational motion and its translational motion. So here we have a video. This is a close-up of what one of the scans looks like. It's like it's going down through it. And as you can see, they change shape and size. There's also one axis of rotation through the bead so that you can track the orientations. So the different sizes and the different shapes of it allow us to figure out where it is and how it's moving throughout time and the oscillations.
So then on the simulation side, we use a piece of code called Peekity-Grav, which is primarily used for studying collisions of aggregates in space, so asteroids and planets, all sorts of fun things like that. It's a soft sphere code, so it allows for small overlaps of the particles, which is a big part of how it calculates the simulation. And most importantly for us, it allows for the manipulation of all sorts of materials parameters, so we can change all sorts of things about our system and kind of see how that affects it. So in terms of the simulation setup, we have a kind of diagram on the side, but I'll also show you a video so you can see what's happening. So we start by filling our box using a little funnel, and it's very satisfying to watch. And then we let the particles settle a little bit, and then we apply a pressure on the top, which is equivalent to the weighted wall. And then we'll shake the system a little bit to let the particles settle into the corner and be a little bit more evenly distributed. And then we'll start oscillating the sidewall just as is done in the experiment. So
here we have the translational movement that is like shear. So with reference to the initial frame, we can see that for this side is the experiment, and it's moving away from its initial position, but then it starts to revert back every time there's an oscillation. With the simulation, you can see a lot more clearly where each oscillation is, but it's about the same shape in that it starts off small and then it grows up. This is only about the first 20 oscillations. So you would see that it starts to steady out, and this implies that there's reversibility in the system. And that means that as you'd push on the system, and the macro state of the granular system would return back to its initial position. And here we have the interval displacement, which this is still the translational movement, but that's between each oscillation. You can see how it moves. So once again, the experimental data is a little bit noisier, but the simulation, you can see that it starts out large and then it goes down to a steady state. So it's about moving the same distance each time.
So then looking at rotational movement, once again, you can see that the experiment data is pretty noisy. And again, if you looked at it for more oscillations, you would start to see a more similar trend to what we see in the simulation. But the simulation shows pretty clearly that the displacement of rotation is increasing pretty steadily over time. We do expect that this would level out if we went for longer, but the simulation takes a long time to run, so we don't have many more oscillations than that at this point. But this is an interesting result because it's not exactly what we were expecting to come from the rotational movement. And then again, looking at the interval thing, we see something very similar, so we can still see that between each oscillation, the displacement in the rotations is increasing somewhat steadily.
So conclusions are that the translational movement reaches an equilibrium. This is what I was talking about with the reversibility. So the system with the forcing stays pretty much the same. And then with rotational movement, so with the simulation, you can see that there's a steady increase. And once again, this is something interesting that we're finding out. And the experiment, as of right now, is somewhat inconclusive, just because we looked at a very small sample size for the oscillation number, and it's kind of noisy. So
looking forward, the main things we want to do is make some improvements on the experiment. One of which would be to get particles with two axes, because right now we're only able to track one axis of rotation, which may be part of why the rotational data is so noisy for the experiment. And another thing would be to get a fluid that has a better index match to the particles, because right now it's not a perfect match, which causes some significant noise in the images. Another thing, we have longer test runs, especially for the simulation, so we can see what the long-term trend of the displacements is. And finally, to change the material parameters a little bit with the simulation to kind of explore how those will affect the system. And finally, we'd like to say thank you to all of these people for helping us out with our project.